Okay, I guess we can get started. I'm very pleased to introduce Harrison Gaebler from University of Kansas. Harrison is a graduate student. He's graduating this summer. Interestingly, though, he's in PDs, I think, and he does this in his spare time. so he's solving bonus space problems in his spare time, I guess. And he's speaking on asymptotic geometry of bonus spaces that have well-behaved Riemann integral. Harrison?
Sure. Well, thanks, Benjamin, for inviting me to this. It really is a privilege for me to speak at the seminar. Yeah, you're basically right. I have been doing this kind of in my spare time. So, when I first came to graduate school, my advisor had me read this book on operator semigroups. And I just found myself asking Banach space questions instead of PDE questions. So that's where this project kind of came from over the course of a few years. And yeah, so I'm going to talk about the asymptotic geometry of Banach spaces that have a well-behaved Riemann integral. And this talk is based on a paper that is going to appear later this year in Real Analysis Exchange. So basically, there are three separate things I want to talk about. The first thing I want to give an overview of what's called the property of Lebesgue in Banach spaces. And this part is not very difficult, but I don't think it's a topic that gets a lot of attention. So I want to just make sure that I cover it. And a lot of it basically is the type of thing that you might see in undergraduate analysis course until the sort of connections to asymptotic geometry arise. But I wanted to just introduce the topic. And then I wanted to show how it's connected to asymptotic geometry and talk a little bit about the three results that I'm going to have in this paper coming out later this year. And from there, what are sort of some of the directions for future research that kind of link up with some themes that are already existing in Banach space theory. So Riemann integrability of Banach value functions. So if X is a Banach space with respect to some norm and F is a function from the unit of interval to X, then a partition is just what you would think. It's a finite strictly increasing sequence of numbers starting at 0 and ending at 1. And just to fix the standard notation, this delta P of I is the length of the ith subinterval. And I used pi P to denote the max length of a given subinterval. And if P is any partition of unit of interval, then you can choose tags inside these closed subintervals, Pi minus 1 to Pi. So there's this pair, PT is called a tag partition, and then you can form the Riemann sum of F with respect to this tag partition, which is this vector here, this sum from I equals 1 to D of the length times the, well, quote unquote height, although it doesn't make much sense, it's a Banach value function, I suppose. But then we get this definition, which is the same definition as usual, but we just replace the absolute value bars with the norm of the Banach space. So the function from the unit interval to X is Riemann integrable if there exists a vector, so that for every epsilon, there's some delta, so that the vector and the Riemann sum are close whenever the partition is length less than delta. So this R01X is the set of Riemann integrable X valued functions on 0, 1. So pretty clear is that the Riemann integral functions are subspace of the bounded functions on 0, 1. And the map from X to the vector, the unique vector XF is linear, and it's the Riemann integral of the X valued functions on 0, 1. What's less clear, but very important actually for this talk, is that you can replace the tagged partitions with interior tag partitions where these tags are restricted to the interior of these intervals. This, it's just a lemma in my paper, and also in another paper, but it's a technical lemma, but it's actually very important. And so if X is finite dimensional, a function is Riemann integrable if and only if it's bounded and Lebesgue almost ever continuous. And then finally, Riemann integrability is equivalent to a Cauchy criterion, which says that for every epsilon, there's some partition such that the difference between any two tagged partitions over the same partition with arbitrary tags is small. And this Cauchy criterion holds only if X is Banach. So I should have mentioned that the definition of Riemann integrability actually makes sense for any norm vector space, but it's only equivalent to this Cauchy criterion if X is a Banach. And this Cauchy criterion is how Riemann integrability is related to Darboux integrability for Banach valued functions as well. So for Darboux integrable functions, the standard definition from like Rudin, for example, is that your function is Darboux integrable if there's a partition so that the sum from I equals 1 to d of the partition, the subinterval size times the difference between the supremum minus the infimum over this partition is less than epsilon. And this can't be directly generalized because supremum and infimum might not make sense in an arbitrary Banach space, but there's this equality which says that the difference between the supremum and the infimum is actually equal to the supremum of the absolute value of the difference for any compact non-empty subinterval of 0, 1, but in this case we're talking about a partition subinterval. So we can define the oscillation of a function over a subinterval and generalize Darboux integrability in that sense. So this is the notation I used for my paper, which I think many people define oscillation at a point, but it was convenient in the paper to talk about oscillation over a subinterval and then let the size of the subinterval go to 0. So in particular, the oscillation is the supremum of the set of absolute value differences where S and S prime are in this interval, which is a fixed S0 minus delta to S0 plus delta intersected with 0, 1. So if you choose the n delta at S0 to correspond to your partition subintervals, then you can generalize the usual definition of real value Darboux integrability. So for every epsilon, there's a p epsilon, so that this sum is something equals I equal 1 to d of delta pi omega f and delta I si is less than epsilon, where we choose delta I and si to give us these partition subintervals. And then if f is Riemann integrable, then if f is Darboux integrable, then clearly this Cauchy criterion, this Cauchy difference, because T1 and T2 are just arbitrary partition points, that's less than the sum. And if it's Darboux integrable, this sum is less than epsilon. So Darboux integrability implies Riemann integrability. But the converse is not necessarily true if X is an infinite dimensional Banach space. So I want to talk about that. And it's actually not hard to see. It's just basically a generalization of the Dirichlet function. So if Rn is a listing of the rationals in 0, 1, then we'll talk about C0 first. But if we define f from 0, 1 into C0 by f of Rn is equal to the nth element of the usual unit vector basis in C0 and 0 otherwise, then the Riemann sum is just equal to the norm of the Riemann sum is equal to the C0 norm of this sum. And if you can imagine for a moment, at each tag Ti, I'm either going to get a distinct element of the basis or I'm going to get 0. So supposing I get an element of the basis, the most this norm can be is just the maximum of the partition, or this is going to be delta pi at any ith term. So this norm is actually just less than the size of the partition, and I can choose this as small as I want. So this function is clearly discontinuous everywhere on 0, 1, but actually it has Riemann integral 0. So it's an example of a Riemann integral everywhere discontinuous function into an infinite dimensional Banach space. And LP works the same way, more or less, but only for p bigger than 1. So if p is bigger than 1, and for convenience, I've taken this norm to the pth power. If p is bigger than 1, I get this sum again. And so I'm getting the sum of the absolute value of the subintervals, or the size times f of ti. And once again, this is just equal to delta pi to the pth power. But since p is bigger than 1, I can split off this delta pi to the p minus 1, which is less than the max size of the p minus 1. And then I just sum over the length of the subinterval, so I get 1. So once again, this function has integral 0 and is discontinuous everywhere in LP for p bigger than 1, but I can't do this for L1. There's nothing to split off in this estimate here where my cursor is. So this function you would think is not Riemann integrable for L1 and discontinuous everywhere. So before I get back to L1, I think this calls for definition. So the existence of Riemann integral functions that are discontinuous on sets of positive Lebesgue measure merits this definition of the property of Lebesgue. So the Banach space X is the property of Lebesgue, and I called it a PL space if every Riemann integrable function is continuous Lebesgue almost everywhere. The Darboux integral is in general the restriction of the Riemann integral to the Darboux integrable functions, which is sort of interesting because the Banach value Darboux integral, there's no immediate guess what the integral should be. You just define integrability. So the integral really comes from the Riemann integral in the general sense. And sort of interestingly, a full characterization of spaces that Banach spaces that have this property where these two integrals will coincide is an open problem. So that's kind of where I went with this paper. Some authors in their papers refer to Lebesgue's property. I think this is actually more common. But I felt that referring to Lebesgue's property and then talking about LP spaces would be confusing. So I called them PL spaces and the property of Lebesgue. So back to L1, the Dirichlet function example fails because we can't split off a small piece of the subinterval sizes that's going to go to 0. And in fact, looking at this sort of example, authors are able to prove that L1 is a PL space. So Nemirovsky, Auken, and Redzwani proved this, and independently also G.C. DeRocha Filho. And this was actually in his PhD thesis. And both of these were in the 1970s that they proved this. And the same idea in both of these proofs was used later on by Russell Gordon to give the first proof, actually not until 1991, that Searlson space, the dual of Searlson's original space is a PL space as well. And I want to sketch out this proof, which is basically the same in both these cases, because this is where the connection to asymptotic geometry really comes in. So both proofs use the Cauchy criterion for Riemann integrability. And what they did was they showed that if a function is bounded and discontinuous on a set of positive measure, it's not Riemann integrable. And they did this by showing that there's some constant, depending only on f, so that for any partition you can find two tags such that the Cauchy difference is greater than this constant. So the way they did this, one thing I should mention, this oscillation over subinterval, it's not hard to see that f is continuous at the point s if and only if the infimum over all deltas positive of this oscillation is 0. So then the set of discontinuities is the union over all natural numbers of the sets Hn, where set of s with the infimum is greater than or equal to 1 over n. So if all of these had measure 0, then the set of discontinuities would be the countable union of measure 0 sets, and that would contradict that we have positive Lebesgue measure. So at least one of these sets has to have positive measure. Then you can define this set. So the EJ star is the jth biorthogonal functional for the basis of either L1 or Searlson space. And we can define the set of S so that the composition of EJ star with F is discontinuous at S. And if the measure of GJ is greater than 0, then F can't be Riemann integrable, because then the composition would be Riemann integrable. And this EJ star into F takes the unit interval to a finite dimensional space, which has the property of Lebesgue. So we can't have a Riemann integrable function which is discontinuous on a set of positive measure. So we can assume that all these GJs are equal to 0, and so their union is equal to 0, or has measure 0 as well. And then for a given partition, we can define this set AN0, which is basically the set of partition intervals whose intersection with this HN0 set, taking out the union of all these GJs, has positive measure. So AN0 has to be non-empty, or else HN0 minus G has measure 0, which it doesn't. So Right. So AN0 is the set of I such that the measure of pi minus 1 to pi, the open interval, intersected with HN0 minus G, has positive measure. So we can look at the R members of AN0, where R is less than the number of intervals in the partition. And we know that EJ star F is continuous at S1 because we've taken out, if I go back, we've taken out the set G where any point where any EJ star circle F would be discontinuous. So we know that this finite sum so let me back up a little bit. Each EJ star circle F is continuous at S1. And the infimum we know at S1 of omega F and delta S1, the infimum over all deltas positive is greater than or equal to 1 over N0. So we can choose a delta 1 small enough and points U1, V1 in this interval and delta 1, S1, so that this finite sum of continuous functions, which is still continuous, is less than epsilon, where Z1 is F of U1 minus F of V1. And because this is the infimum over all deltas of the supremum, we can choose U1 and V1 close enough that this continuity bound holds, and also that this norm is greater than or equal to 1 over 2 N0. And it's important here that this M0 we can choose arbitrarily. So we just fix an arbitrary M0. And then we can pick an M1 greater than M0 so that the tail is of this series is less than epsilon as well. And then we continue this process. So we do the same thing for S2. So we can choose U2 and V2 so that the norm of Z2 is greater than 1 over 2 N0. And that the sum to M1 of these finitely many continuous functions, which is still continuous, is less than epsilon over 2. Choose M2 bigger than M1 so that this next tail is greater or less than epsilon over 2. And we repeat this process. So in general, for each k, we can find a UK and VK in some interval and delta k for delta k as small as we want, which is contained in the subinterval, so that ZK is greater than or equal to 1 over 2 N0, where ZK is this difference of F of UK minus F of VK. And the sum to MK minus 1 of EJ star ZK is less than epsilon over 2 to the k minus 1. And each MK is chosen greater than MK minus 1 so that the tails are small in this sense, as epsilon over 2 to the k minus 1. And so then we can define our tags so that if I is not in this AN0 set, so if I'm not in these partition intervals that intersect with my sort of bad oscillation of the functions, those intervals, I can just set the tags equal to each other so that my Riemann sum will give me 0 there. And if I should say k, not I, this should be a k. If k is in this interval, then I can take T1 to be UK and T2 to be VK. And so then the Cauchy difference gives me the sum from k equal 1 to R of P, IK, and ZK, where again, ZK is this difference. So it follows that we can split up the ZKs into this infinite sum, and then we take off the first part, which is less than epsilon by continuity, and the last part, which is less than epsilon because we chose MK large enough that the tail is less than, well, epsilon over 2 to the k minus 2. So those just go away by the reverse triangle inequality. And then we're left with this sum, K1 to R delta P of IK, the sum from MK minus 1 plus 1 to MK minus 1 of EJ star ZK EJ, minus this thing, which is small. Now, here's the connection to asymptotic geometry. Other than the fact that we could choose M0 arbitrarily, in addition to that, for both L1 and Searleson space, we can move this norm inside the outer sum up to some constant out here. And so now we have this this block sequence, and adding back in the two pieces that we took out before, this guy is, I should say, bounded below by ZK minus epsilon over 2 to the k minus 2, where we've taken out the small pieces again. And then zk was bounded below for each k. The sum of the delta p ik's is bounded below by the size of the set of positive measure. And then you choose epsilon small so that the rest of this is small. And we get some constant that depends only on f, since the size of this hn0 set and d on f. So what we've
So I have a
shown.
question. What exactly are you using from Zilson here? Is it like they behave like little L1 ends, or?
Say it again. I didn't hear that.
Sorry. What did you exactly use? Which property of Zilson did you use there? For this, 3 is smaller than.
So I'm really using the fact that it's asymptotic L1.
Oh, I see. Like n guys after the nth place are like.
Yeah, because
okay.
M0 is arbitrary.
Yes. Okay. Yes. Okay. Thanks.
So what we showed is that a bounded function just continues on a set of positive measure in L1 or a Searleson space can't be Riemann integrable. So both of these spaces have the property of Lebesgue. And so this observation that all we're using really is the property that it's asymptotic L1 with respect to the basis. In 2008, K.M. Narlenkov proved that every asymptotic L1 space, if it's asymptotic with respect to a basis, has the property of Lebesgue. And this is sort of an interesting problem in characterizing these spaces. There really hasn't been a whole lot of literature about this. And in looking at all the papers I could find, so Russell Gordon published his paper in 1991, and there really wasn't much published on this until, I mean, maybe a paper or two, but there wasn't much until 2008. So a big gap. So I actually was unaware of this paper, and I made the same observation in looking into these properties that Narlenkov did, and I had the same proof that he did, which is basically the same proof we just saw. It's exactly the same proof we just saw, that every asymptotic L1 space with respect to a basis it has the property of Lebesgue. So I reproved his result and got really excited, but then found his paper. So instead, I was able to generalize this to asymptotic L1 spaces that are asymptotic L1 in the coordinate-free sense. So just so everyone recalls, the set COFX is the set of closed subspaces in X that have finite codimension. And so because it's finite, because these spaces have finite codimension, they're complemented in X by some finite dimensional space Z. And so there are bounded linear projections onto Y and Z where X has this unique decomposition. And you can more or less do the same proof. And so just to be, before I get to that, I said that the space is coordinate-free asymptotic LP. If there exist constants, such for every n, you can find subspaces of finite codimension so that this inequality holds for all yi in each subspace y. And it's important, I didn't say it in my definition here explicitly, but these subspaces and vectors have to be extracted in a specific way in an n-turn game of 2 players so that it actually generalizes the notion of being asymptotic LP with respect to a basis. So using this definition, I was able to show that every asymptotic L1 space that's coordinate-free asymptotic L1 is a PL space. And the proof is much the same. The projections onto finite dimensional spaces play the role of the coordinate functionals. And instead of splitting the sum into like a piece that's small by continuity and a tail space that's small and a block sequence, the splitting is just you project onto the subspace Y and the subspace Z. And then because each of these projections is continuous, you get the same continuity argument for the composition of PZ circle F. And then you can bound the sum from K equal 1 to R of PY below because of this estimate, because once you project onto subspaces Y, you're inside these finite codimensional subspaces. And so you have an estimate like this. Also, the argument that the set GJ had to be measure 0 in the proof generalizes to the fact that the sets, the set of points where PZ circle F is discontinuous, the same argument shows that that has to have measure 0 as well, because the ZIs are finite dimensional spaces, so they all have the property of Lebesgue. And I think that this is actually the optimal sufficient condition for the property of Lebesgue for a few reasons. The first is that the property of Lebesgue is a global condition. Obviously, if a space contains a subspace that doesn't have the property of Lebesgue, then the whole space can't have the property of Lebesgue. And also these ZIs, as long as they're finite dimensional, they can have extremely large dimension. The only requirement is that it's finite. And maybe the most compelling piece of evidence is that there are sequence Orlitz and Laurent spaces that are similar to L1, but that aren't asymptotic L1 and are not PL spaces as well. And so there's an example of that, which was in Gordon's paper. And one of my results I'm talking about later actually lets me reprove that result in a different way. And so that sort of brings me to the local asymptotic consideration. So the point being is that we're searching for this characterization of the property of Lebesgue, and I think this is the optimal sufficient condition for that to happen. So locally, in the same paper, Narlenkov credited Pelczynski and Dorota Filho with the following unpublished result, which is that every spreading model of a PL space is equivalent to the L1 unit vector basis. And Narlenkov gave a proof of this in his paper as well. And it uses a specific enumeration of the dyadic rationals in 0, 1. And here's where the interior tag partitions become important. So I'll get to that. I'll say why probably on the next slide. So what his method was that if VI is a spreading model generated by a normalized basic sequence, then he defined this function where Rn, it was the nth point of the nth item in the enumeration of the dyadic rationals, where he defined f of Rn to be this difference in the sequence xi, and 0 for s's that weren't dyadic rationals. And what he showed was that if f is not Riemann integrable, that implies that this lim sup is positive, and that's a sufficient condition for the VIs to be equivalent to the unit vector basis of L1. So I want to sketch this proof. So what he did was, for a contradiction, suppose that this lim sup is 0 and choose n so that the sum over 2 to the n is less than epsilon. And he let P be a regular partition with 2 to the n plus 1 terms. The regular just means that the interval sizes are all the same. And then choose tags in this partition so that you have an interior tag partition, okay? So then the Riemann sum is equal to pulling out the 1 over 2 to the n. We get the sum over all k, where the tags are dyadic rationals of f of tk, which is equivalent to 4 here. And I've said that T1 through TR correspond to the enumerations Rn1 to Rnr in lambda, which is the dyadic rationals. So the key here is that if I'm going to make this small by comparing it to this spreading model, this estimate with the spreading model up here, I need the n1 to be far enough along the sequence, basically. So first of all, because this sequence xi is basic with some basis constant called kx, 4 is less than or equal to these 2 to the n plus 1 terms. And the specific enumeration that Narlenkov used was really clever, because what it does is that it forces the first 2 to the n minus 1 enumeration elements to correspond to the partition tags P1 through P to the 2 to the n minus 1. And then because we chose the TIs to be an interior tag partition, that forces this n1 to be greater than or equal to 2 to the n, because it's not a partition point. And so that means that this sequence is far enough along that we can replace this norm by by epsilon over 2 to the n plus 1 times plus the norm of this difference in the elements of the spreading model. And so the spreading model is 1 spreading, obviously. And so this is less than or equal to twice times this v1 minus v2 to minus v2 to the n. And this gets us what we want because we assumed that this norm over 2 to the n is less than epsilon. And this epsilon to the n plus 1 can be small as well. So this was his proof that every spreading model of a PL space is equivalent to L1. So then the natural question to ask is every asymptotic model of a PL space also equivalent to L1? So if I got an array of normalized basic sequences, it's L basic if the diagonal sequences like this are L basic as well for high enough indices. And then this array, it generates an asymptotic model if I have an estimate like this for some epsilon n going to 0. And so some remarks. Asymptotic models are obviously generalizations of spreading models where if you've got a normalized basic sequence generating a spreading model, if every row is that same sequence, then you have an asymptotic model that is just the spreading model. And I should say asymptotic models were introduced by Halbis and Odell. And the proof, Narolinkov's proof for spreading models and the subsequent lemmas that show that this condition that proves is sufficient for the spreading model to be equivalent to L1, they depend heavily on the fact that this VI is 1 spreading, or at least equivalent to a 1 spreading sequence. You can make that relaxation. Or say equivalent to a C spreading sequence, I suppose. It doesn't quite have to be 1 spreading. So I thought it was reasonable to expect at least that every 1 spreading asymptotic model of a PL space is equivalent to L1. But the issue is how to define this function f. So in my paper, I had the same enumeration of the dyadic rationals, and I defined f like this, where these squaring the exponents meant that for each interior tag, no matter what my interior tags were, I would get a subarray of distinct rows. I call them columns in my paper, but I think rows is maybe more natural because that's how it was introduced by Halbis and Odell. So squaring the exponents means that no matter what tags we choose, I'll get a subarray of distinct rows. And the dyadic rational technique means that if I go back to 5, back here, I can have a lower index that's far enough along in relation to the row number. The issue is when I choose arbitrary tags to show that my function is Riemann integrable for a contradiction, I get a subarray where I'm deleting rows, but there's no control over which rows get deleted. So the issue then is how to repeat the spreading model proof when I have no control over the deleted rows. And I couldn't get around this hurdle by just trying to redefine f in a clever way. Maybe there is some way to do that, but I didn't find it. So I ended up defining a particular class of asymptotic models to solve this problem with deleted row, which I called SP asymptotic models because they basically resemble spreading models. So I said that VI is an SP asymptotic model if it's 1 spreading, the asymptotic model is 1 spreading. If every subarray with deleted rows is L basic and generates the corresponding sub-asymptotic model, which of course is equivalent to the original one. And if this generates an asymptotic model, I get some decreasing sequence of epsilons going to 0. And as long as the supremum taken over all these subarrays that generate asymptotic models, as long as the supremum is less than some uniform constant, then the same proof will work as for spreading models. So in short, what I'm requiring is that every finite diagonal sequence of sufficiently high index is L basic and close to the corresponding terms of VI. I think the supremum is just sort of a technical condition. Pretty easy to ensure. So with that, every SP asymptotic model of X is equivalent to the L1 unit vector basis if X is a PL space. And this SP asymptotic models obviously also include spreading models. So that was the second result. The third result is possible because there was a really remarkable result this past year from Corey Krause, who I think might even be on this Zoom call. And so this is just there were a lot of results in this paper, and this is just part of one result. But if I've got a basis for X so that every normalized block basis generates a spreading model, then X is asymptotic LP with respect to that basis for some P. I believe it's actually one asymptotic LP with respect to EI for some P. So this has the following corollary. If I have a Banach space with a basis so that every normalized block basis generates a spreading model, then X is a PL space if and only if it's asymptotic L1 with respect to that basis. So obviously, if it's asymptotic L1 with respect to the basis, then it's a PL space. But if it's a PL space, then its only spreading model can be L1. So it can't be asymptotic LP for P not equal to 1. So this is a pretty immediate corollary. And it provides alternate proofs as to whether or not X is a PL space, at least in the case for LP and DW1, the Laurent sequence space. So this is one of these spaces that I was talking about that is relatively similar to L1, but not asymptotic L1, and it's not a PL space. And you can show that I provided this proof in my paper as well. So several directions for research. Some of them are probably easier than others. So one direction is to, the obvious thing is we want to relax this SP hypothesis to prove that every spreading asymptotic model is equivalent to the L1 unit vector basis. And my guess is that this is true. It may be there's some, it certainly will require, I think, some additional techniques than what was used in the Narolenkov proof and in my proof for the SP asymptotic models. But I think it's probably possible. There might be some other combinatorial technique that could be useful here. I'm not sure, but I think it's possible to do this. And the other thing to do is to derive sufficient conditions for X to be coordinate-free asymptotic L1 in terms of asymptotic models. And this is a much harder problem. So there was a paper last year from Argyros and Watakis where they showed that a unique asymptotic L1 asymptotic model with respect to normalized weakly null arrays is not enough to say that the space is asymptotic L1 in a coordinate-free sense. And it's actually very strongly not enough. They showed a really remarkable result. My guess is that there's some sufficient condition where you have a unique asymptotic L model with respect to normalized weakly null or normalized block basic arrays, and probably some additional hypotheses. And maybe those additional hypotheses involve the fact that X itself has the property of Lebesgue in some way. But I'm just not sure at all what these hypotheses would be. So it's more difficult, but I think it ties in with the sort of long-standing open questions of upgrading these local asymptotic results to some sort of global result about the space as a whole. And I also wanted to talk lastly about some evidence based on distortion that a characterization that PL spaces are really just those spaces that are asymptotic L1. So there's already some evidence for that with the result from Corey Krause and the corollary that we just talked about. But if we recall that, so X is lambda distortable for some positive, or lambda greater than 1, if there's an equivalent norm on X so that lambda is less than the supremum of this ratio for Y and Y prime in the unit sphere of Y, for all closed and infinite-dimensional subspaces Y and X. And if X is lambda distortable for every lambda greater than 1, then X is arbitrarily distortable. So I should mention here, it's obviously a long-standing problem to try and find a Banach space that is distortable for some lambda greater than 1, but not arbitrarily distortable. And I don't think the property of Lebesgue is deep enough to help with this, because L1 is obviously not distortable at all, but it's a PL space. And there are certain arbitrarily distortable PL spaces that are Searleson-like spaces. And I think this was shown by Andrew Locus. And I think I found these in the paper as modified mixed Searleson spaces. But there are PL spaces that are both distortable and non-distortable and arbitrarily distortable. So I don't think the property of Lebesgue will help with this problem. However, there's a well-known result is that if X has no arbitrarily distortable subspace, then X contains an asymptotic LP with respect to some basic sequence subspace. So this has the following corollary. If X is a PL space, then at least one of the following is true. If X contains either X contains an arbitrarily distortable subspace, or if it contains no arbitrarily distortable subspace, then it contains an asymptotic LP subspace. But since X is a PL space, that can only be an asymptotic L1 subspace. So in particular, one interesting thing to note is that if you could construct a PL space with no asymptotic L1 subspace, then this space would necessarily be arbitrarily distortable. But there's a lack of arbitrarily distortable PL spaces that are not already asymptotic L1 in some sense. These options are not mutually exclusive. So I think that this sort of indicates that PL spaces probably at least have an asymptotic L1 subspace with respect to some basic sequence. There's some global structure that has to happen that makes these spaces close to L1. And so I think that provides some evidence that CF asymptotic L1 is the optimal decision condition, and that there's just this gap in what we know about upgrading local asymptotic structures, even strong ones, to global structures, and that gap has yet to be filled. There's also a lot that hasn't been done on, like the Krivine set of a PL space, or the finite representability of L1 in PL spaces, stuff like this. I don't think there's any work done on that. And I think it's also important to note, and this can be found in our Lenkov paper too, that PL spaces, there's a distinction between PL spaces and Schur spaces, even though Schur spaces also have a unique L1 asymptotic model, or sorry, a unique L1 spreading model. Narlenkov constructed a Schur space that is not a PL space, and it's based on the James tree space. Did this. I think Richard Hayden also constructed a Schur space of this form that's not a PL space, and I think they basically followed the same construction, but the spaces are slightly different. So yeah, this is still an open problem, and so that's about it. But I'd like to thank you all for listening to my talk. And as Bunyamin said, I'm a graduate student, so and I'm graduating this summer, so I have a lot of work to do before I can defend. A lot of work to do on PDEs. So I'm hoping to continue this going into Banach space theory in the fall. I'd really like to continue that direction for my research career, and I've pretty much reached my limit of my ability to work on this problem by myself as a grad student. So if you have any interest in working on this characterizing PL spaces or these local to global type asymptotic problems, feel free to email me. And I'd like to start this research up again in the fall. And I should also mention the preprint for my paper is not on the archive, but if you'd like a copy of the preprint, just send me an email and I'll send you the preprint. Just some papers. These are the papers I cited. This is Russell Gordon's famous survey paper, Riemann integration of Banach spaces. And there are lots of other more recent papers that can be found in my paper. And I think my paper is going to be online this summer, maybe July, I think is what I was told. But yeah, that's my talk. So thanks for listening.
All right, thank you so much, Harrison. That was very nice, very interesting question. I assume we have a bunch of people who already solved the problem now, so let's hear from them. Anyone?
Well, thank you very much for this nice talk. This is Gaebler from Paris. Well, I enjoyed all of this very much. I have a question that may be very simple. Since you have these asymptotic properties for in relation with property of Lebesgue, do you know, maybe this is simple to check, whether you have some stability of the property with respect to nonlinear equivalence? That is, if you take two spaces which are Lipschitz equivalent or uniformly homeomorphic, and one has property of Lebesgue, does the other one has property of Lebesgue? Did you consider this?
Not a lot. I did consider the question of if you have like a bi-Lipschitz map between the PL space and some other space, then I think that does have to preserve this property.
Okay.
But no research has been done on that. I don't know anything more than that.
Okay, and maybe uniform homeomorphism could be a little harder, but it seems like the natural thing to try, maybe.
Yeah, that makes sense.
I have two short comments also about the notation PL space. If I remember correctly, but I'm not absolutely sure, that terminology was used in the context of complex uniform convexity in the 80s. So maybe check this. It should be easy to do is Google whether PL or PL convexity already exists. If it does, it deserves to be mentioned somewhere in the paper.
Right.
Sure, but it rings a bell some time ago, before you were really born, probably. So,
yeah.
And speaking about old stuff, around 1980, there has been work by Talleyrand on Riemann integrability. I mean, he produced a lot of work, everybody knows that. But he worked on Riemann integrability about 40 years ago. And it was rather in the context of harmonic analysis. So certainly you have nothing like asymptotic theory of Banach spaces. So it's not directly related with what you did. But since it's certainly non-trivial, it may be safe to have just a look on what he did at the time. So it's again Talleyrand, maybe with one co-author, I'm not sure, around 1980.
Okay, thank you.
You're very welcome. Thank you.
Okay, thank you. Anybody else? I think the Gilles question is very important for the nonlinear one. The first thing probably will be to check is whether that counterexample, that Dirichlet function, can be transferred with the Lipschitz functions, or even, my guess is you can do it even with more general functions. So that's a good point. The other thing I wanted to say is that it seemed to me that, I mean, following the proof, what you need is something like, you look at the space and you look at the trees, like let's say Wickli-Null trees, and then it seemed to me that if your condition forces that every Wickli-Null tree has a branch which is sort of like asymptotic L1 or something like that. And if I remember correctly, this already implies, right, Thomas, that this will imply that it will embed into asymptotic L1 space. Or you might need reflexivity for that.
Say again, you kind of caught me.
So every Wickli-Null tree has a branch which is asymptotic L1.
Yeah.
Will that imply that it embed into asymptotic L1?
This is, okay, so these things are equivalent, but then you need a separable dual, if I remember
Okay,
well.
yeah, so.
This is what I actually, this comment that between the coordinate free and the coordinate thing, that you can always, but only under certain condition, when you have the coordinate free asymptotic property, you can embed it into some space with a basis which has the basis property, the corresponding base property. But this is not in general true. You need some like separable dual or things like that.
Kind of condition, right?
Yeah, you need some.
I think you may want to check that, because if the space doesn't have that property, if you look at the Dirichlet function, right, on rationals that you send onto this tree, then some branch has to have, like, it will violate this, just like the Pelczynski's spreading model proof, right? So, and so that might already imply under that case that space has to be asymptotic L1. That's my guess. But any other comments?
There's a question. It says, are the coordinate-free asymptotic properties I mentioned same as or related to AUC and or AU asymptotically uniformly convex source?
Yeah, AUC is one of these asymptotic properties, right? Right.
Mhm.
It's all these asymptotic properties, they can be defined in terms of games, as you already said, right?
Mhm.
And usually under certain condition, you can always embed a space with some asymptotic property into a space with a basis with the same asymptotic property. But when you're close to L1, this doesn't work because you need, like, for example, you usually need separable dual or things like that. So this is why you, yeah.
There's also a question that says, ask me to communicate my email ID. Do I send that to all panelists or all panelists and attendees? I'm not sure.
Say it again. I don't know. What's that?
Somebody asked me to communicate my email address, and it gives me the option to send it to all panelists and attendees.
I think if they just Google your name, right? So
yeah, that's true too. Yeah, I have a website at KU.
Yeah.
Yeah, so what Thomas pointed out is interesting because unfortunately this property doesn't seem to distinguish reflexivity. So that's
exactly. Yeah.
Right.
So, but it's a good problem. Okay. Okay.
Yeah, but one could ask, like, say, let's take a reflexive asymptotic L1. I mean, is it among the reflexive spaces equivalent, right? I mean, this could be
yeah, that's my guess. That's why I think what I said about
there you have more chances to prove equivalence of that. Yeah, I think, I mean, in some better class of spaces.
Mm-hmm. So it seems like the thing to do is look at branches of weakly null trees and
let's say you have a Banach
spaces.
space with a separable dual, or even a reflexive, then you have more structure. Then you have more theorems also to use between the asymptotic property and
Okay. Thanks again, Harrison. That was very nice.